Hi everyone, I'm Dr. Surjit Singh. In this video on Python by examples, we shall talk about stack implementation of linked lists. Let us begin. In this session, we will learn about the stacks. Like queues, node objects will be the building blocks for the stacks that start with the top pointer. We'll learn about the push, pop, peek, and traverse functions and use them as methods of the stack class. IsEmpty is used to know if a stack is empty or not. Similar to a queue, a stack is a linear data structure. However, for stacks, items are added and removed from only one end. For example, consider a book rack. We stack books on it on top of one another. This creates a stack of three books. In this arrangement, we cannot pick the books B or A as long as C is lying above them. To remove B, we must remove C first. Turn of A comes last of all. Such an arrangement is called a stack. Stacks follow the principle last in first out that is known as LIFO. So for stacks we require only one pointer, that is the top of the stack. Push adds an item at the top of the stack while pop removes the item present at the top. Another pop on this stack removes C. Two more pop operations remove B and A. Stack is now empty. One more pop on this stack will return none. In the previous video on queues, we learned about the linked lists which are based on the node class. We will reuse the same node class here. However, this time we will organize the nodes to function as a stack. The init function serves as the class constructor that gets memory to hold an object of the class node. Data and next are the two attributes of the node. The address of the node is saved in a local variable self, which is always the first parameter of all the member functions of a class. In Python, member functions are known as methods of the class. We provide the data parameter at the time we create a new object of the node class. The first statement of init method stores this data in the data attribute of self. In Python, we write it as self.data. In the next statement, we assign none to the next attribute of self. With this, the node object is constructed and the init method concludes. Constructors always return self, which is the address of the newly created object. We use it as a reference to this node object. Top is none for an empty stack and its size is 0. In our previous video on queues, we had discussed the traverse function. We will use it for stacks as well. This allows us to have a look at the stack at any stage of its construction. The push function is used to add a node to the stack. Before calling the push function, if we call the traverse function, we get this output that tells us that the stack is empty. On calling push, we provide it with data that is saved as local variable of push. We have already declared top and size in the main program that we can use within the push function also. However, if we need to change their values inside the push function, we have to declare them as global variables. With each push operation, the size of the stack increases by 1. The node function calls its init method to create an object of the node class. Data value of push function is passed to the data parameter of init. First statement of init passes this data to the data attribute of self. Second statement saves none in its next attribute. At the end of init, it returns the address of this newly created node. It is crucial to save this address in a variable immediately, otherwise the reference to the node is lost. We save the address of this object of the node in a local variable new node of the push function. Such variables as hold the address of some other variable are called pointer variables or reference variables. The current value of top is copied to the next attribute of new node. Since this is the first node of the stack, even top is none. Finally, top is updated to the variable new node. With this, the node is successfully added to the stack. The push function ends and the memory used during its execution is released. If we now call the traverse function, we get this output. When the push function is called once again, the stack size increases to 2. A new node is created with B as its data and its address is stored in a local variable new node. The next attribute of new node is set to the current value of top. It means both of them now point to the node A. Finally, in the last statement of the push function, top is updated to new node. This means that now top also points to node B. With this, the execution of the push function ends once again and the stack now has two nodes. The traverse function confirms this. One more push operation proceeds as follows. Traversing the stack again confirms that we are on the right track. Now let us define the pop function. This function removes the top item from the stack and returns its data. The returned data can be used in the main program. Here we simply print it. The top and size variables are updated within the pop function also. For the current stack, top is not none, so we reduce the size of the stack. We copy the data attribute of top to the local variable named data, which gets the value C. After this, we update top to refer to its next node. Since node C no longer has any reference to its memory, it becomes a dangling node and is reclaimed during the next cycle of the garbage collection. We have restructured the stack and will now return the data value that is C at the end of the pop function. The print function receives C returned from pop and displays it. The next pop operation further reduces the size of the stack, stores B in the data variable, moves top to the next node, deletes the dangling node, and returns B for printing. The third pop reduces size of the stack to 0 and saves A in data. Top now becomes none, dangling memory is cleared, and it returns A for printing. Fourth pop finds top to be none, so we execute the else part of the pop function and return none without changing top and size variables of the stack. Print function receives none and prints it. Stacks are used in many computer science applications. Let us recall the push function once again. Main function calls the push function. During its execution, the push function further calls the init function of the node class. These functions end execution in the reverse order. After conclusion, init function gives control of execution back to the push function. At the end of the push function, control goes further back to the main program. It is clear that Python maintains stacks to manage the control of execution of the functions. Fortunately, Python handles these memory stacks automatically, so we do not have to worry about them. In the 10th video on this series of Python via examples, we also explored recursive functions. The computer uses a call stack to manage their execution flow. When a function is called recursively, the calls occur in one order and finish in the reverse order. Recursion relies on the stack to track these nested calls. Peek function returns the top item of the stack without removing it. In this part of the program, we will print the value returned in peek. If top is none, peek returns none and we print it. Let us now push a few items to the stack. The top is no longer none. If we now call the peek function, it runs the else part of the peek function to return the data component of the top node. we may note that stack is not affected by the peek function. Size of the stack changes dynamically in push and pop operations. We can print size of the stack at any time we like. Managing multiple stacks in a program becomes straightforward if we define stack as a class. Top and size are now data members of the class, while push and pop become its member functions. In Python, data members are known as the attributes of the class, while the member functions are known as the methods of the class. In these methods, self is always the first parameter. The prefix self dot is used with all data members to assert that each object of the class accesses its own set of attributes. Stack function creates an object of the class. For this class, we are not required to pass an initial parameter, so we do not need any init function. Instead, we initialize its attributes to their default values. We assign none to top and 0 to the size attribute. We save the reference to the stack object in a variable and name it chemistry. This means that chemistry.top is none while chemistry.size is 0. Similarly, we create another stack object and name it physics. First, we push a book named organic onto the chemistry stack, increasing its size to 1. Next, we push optics onto the physics stack, followed by inorganic onto the chemistry stack. Let us now pop out a book from the chemistry stack. Inorganic book pops out and we print it. The next pop operation removes the organic book from the chemistry stack and we print this also. The third pop attempt from the chemistry stack returns none for printing and the stack size remains 0. Performing a pop operation on the physics stack pops out the optics book. At this point, both the stacks are empty with their sizes at 0. Often, we need to determine whether a stack is empty or not. To do this, we add a new member function to the stack class called isEmpty. A stack is empty if its size is 0 or if its top is none. Since checking if top is none is faster than comparing two integers, we simply return top is none. Note the prefix self dot before top. Let's apply this function to the two stacks of the books shown here. Printing the result of chemistry is empty returns false, while physics is empty returns true. In this session, we introduced the use of linked lists to implement a stack and developed its push and pop functions. We learned about the stack as a class, about empty stack, and about the methods of the stack class. We also discussed about the simultaneous growth of two stacks. Hope you enjoyed the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward to your comments. Please stay tuned for more such videos.